Good morning, chemists. How are you? Are you guys ready to learn about organic chemistry? Remember, we're talking about stereochemistry in this chapter. So hopefully you have got all that in your mind. You can visualize these molecules that are in 3 dimensions because we're going to talk about a lot of that today. So we are starting on 12-5. 12-5. So here we have another reaction. Here's the electrophilic addition of halogens. So we can make what's called a vicinal dihalide. What does vicinal mean? They're in the vicinity of each other. They are neighbors of one another. So it's a dihalide. We have 2 halogens that are on neighboring carbons. And so this is a reaction that we can do with chlorine or bromine. So chlorine or bromine, so Cl2 or Br2 for this reaction, reacting it with an alkene. So why would we make these compounds? Well, they can be used as solvents, they can be used for dry cleaning, and they can be used for degreasing and anti-knock agents for gasoline. So they have their uses, so we have to know how to make these vicinal dihalides. So for this reaction, I said we can use chlorine or we can use bromine. Remember, chlorine is a gas, and so chlorine is a poisonous gas, so it's difficult to deal with. But usually we will carry these out with bromine instead because it is a liquid. We also will carry out the reaction at or below room temperature, and in some kind of a solvent that's inert. It won't react, but it's halogenated. So remember carbon tetrachloride? So we use CCl4. It won't react with anything. It's just our solvent in the reaction. But as I said, we use bromine because it's a liquid. So it's not a poisonous, toxic gas. It's a liquid. And as we're reacting, the bromine itself is a red color. And then when it reacts, when it turns into the vicinal dihalide, it turns colorless. So you can tell it is reacting. You can look at it and swirl it, and when the color goes away, you know that it has reacted. So it turns colorless upon reaction. But here we can see the alkene. One of the carbons gets a bromine, the other carbon gets a bromine to give us this 1,2-dibromohexane. So what is the mechanism for this reaction? How is this reaction occurring? Well, it's occurring by antiaddition. Antiaddition. So remember our synaddition. Both of the atoms get added to the same face in synaddition, either above the plane or below the plane, because remember it's trigonal planar. Our alkene is trigonal planar. But what happens with antiaddition is one atom gets added above and one below. So if one gets added above, then we put a wedge, one below, we put a dash. And so for those 2 carbons that were the alkene, so look at this, cyclohexene, the same thing that you made this week in lab. We could react that further, adding in bromine and carbon tetrachloride in order to get this product by antiaddition. But the product will also form the enantiomer, so we can write that it's racemic. So this isn't absolute, right? Trans is relative configuration, but we could do the absolute configuration of this, and we could add that into the name, but it's just racemic. We get one of them being a wedge where the other one is a dash. So remember for this second one here, pancake flip it over so that you can see how the molecule is the opposite configuration. But look at how the bromines are added in. One is added above and one is added below. So for this reaction, the stereochemistry of the starting material also matters. The stereochemistry of the starting material. We were just talking about what kind of stereochemistry do we get for the product, but the stereochemistry of the starting material is maintained throughout the reaction. So we would say that this is stereospecific because the stereochemistry of the starting material, is it a cisalkene, is it a transalkene? That stereochemistry is maintained. So for the cisalkene, notice that they're both of the methyls are on wedges and both of the hydrogens are on the dash line. And then notice that a bromine gets added above and a bromine gets added below. So this is our antiaddition, right? One bromine added above, one bromine added below. But we can see that we're maintaining the stereochemistry, the cisalkene, we're maintaining that stereochemistry from starting material to product. We could do it the opposite way where we've added now this bromine below and this one above, but we still have the two methyls on the same base. So either both of the methyls on a wedge or both of the methyls on the dash for the cis alkene, so for that starting material. For our trans alkene though, look at this. One methyl's on the wedge, one's on the dash here. And again with the other, one's on a dash, one's on a wedge. But again, we see our bromines added below and above for the two different compounds, giving us the anti-addition. So for this first one that I showed you with the cis starting material, the cis starting material ends up with a racemic mixture of the two enantiomers, right? The RR and the SS. Those two are enantiomers of one another, non-superimposable mirror images. But when we look at this where we started off with the trans alkene, we end up with what's called the meso product. So let's just refresh our memory on what meso means. If I take this and I rotate around this bond, I'm going to leave the bromine here. And I'm just going to rotate around the other bond to where I end up with the bromine here at the top. And so if I end up with the bromine here at the top, as we rotate this methyl that's in the front, as we rotate that down, it's going to end up in the back. If I rotate this hydrogen that's in the back, it's going to end up in the front. You should be able to visualize that. I shouldn't be telling you anything new. But as we look at this molecule, you should be able to see that there is an internal mirror plane. And so if there's an internal mirror plane, that means it is achiral. So we call it a meso compound, where both of these compounds here, the SR and the RS, they are identical to one another. We can rotate it and it will superimpose. And so these are not enantiomers of one another. It's a meso compound, so we only get one product here. Just one product. They're just showing it two different ways, but just one product here where it is the meso compound because these two are identical to one another. So with the cis-2-butane, we would end up with these enantiomers. With the trans-2-butane, we end up with this meso compound. It is not true that every time we have trans, we end up with a meso compound. It's only true that we end up with a meso compound as long as the three things attached to both of the carbons are the exact same. If the three things attached to those two carbons are the exact same, then we have an internal mirror plane that is possible. So we have our anti-addition, and we have the alkene, so the acyclic alkene stereochemistry maintained in the course of the reaction. Questions there? All right. So in this reaction, we're starting off with bromine or chlorine, and we said we usually will start off with bromine. So remember Br2, we call that bromine. That's the diatomic molecule bromine. Cl2, we call that chlorine. So we start off with bromine, and we have this polarizable bond where we end up reacting it. So we have three arrows here. We end up reacting where we end up with this thing called a bromonium ion. And so the two carbons now are sharing bonds to the bromine, where we make this three-membered ring. So you can see the course of the reaction here. Remember, we have this pi bond where we're sharing electron density, this p orbital on each of these carbons. So we have a pi bond, and we take those electrons and we use them to form now new sigma bonds. This is a pi bond. Oh, sorry. This is a pi bond here between these two carbons, and then we end up making two sigma bonds between bromine. So we make this thing called a bromonium ion. a cyclic bromonium ion. So let's look at what the mechanism here. And so for this reaction, we have here, let's say we have a double bond and we have our bromine. And remember, we need to show the bond and we need to show these lone pairs. So this is a polarizable bond, So I'm going to draw it down here, two different cases for what could happen here. Only one of them is true, but I'm going to show you two different cases. So it's a polarizable bond, so we can pull electron density toward one of the bromines. And so if I pull it toward this bromine, then the other one ends up with a partial positive charge. The other one ends up with a partial positive charge. I'm polarizing it. I'm making it into a polar bond. And so what is happening here? Well, we're going to have something that is an electrophile. What would be our electrophile here? Well, our electrophile would be this bromine that has the partial positive charge. Something is a nucleophile. Our nucleophile is the double bond electrons. And then we need a leaving group. The other bromine that has a partial negative is the leaving group, right? This is an SN2-like reaction. We have a nucleophile, electrophile, and a good leaving group. We polarize that bond to give us a good leaving group. And so in this reaction, so now I'm going to draw the arrows for the mechanism. What happens? Our nucleophile attacks the electrophile and the leaving group leaves. If we only did two arrows, then we would end up with this as our product. So bromine is added, bromide has a negative charge. So something has a negative charge, something has to have a positive charge. This carbon here has a positive charge. The carbon that was in a double bond to the other carbon, now it is a single bond, so we have to have a positive charge. But this is what actually happens. What actually happens is our nucleophile, that double bond, attacks the electrophile with the partial positive. The leaving group leaves. And we have an arrow from one of the lone pairs on the bromine to one of those carbons of the alkene. So here we're doing now 3 arrows. So what would be the product if we drew these 3 arrows? Well, with these 3 arrows, now I'm going to get bromine in a bond to both of those carbons. Bromine is now bonded to both of those carbons. So bromine now only has 2 lone pairs because one of its lone pairs was used to make a bond to the other carbon. And so now bromine ends up with that positive charge. Something has to have a positive charge. In one case, carbon has positive charge. In the other case, bromine has a positive charge. And then we still have our bromide ion, right? When it's a negative charge, it's bromide. So what is the difference in these two? Why do we only form one? We only form our bromonium ion because we have octets for all. Whereas over here, this carbon has a sextet, only 6 electrons around it. What's better? Everything having an octet is better rather than having one of our atoms having a positive charge with only 6 electrons around it. So instead of making the carbocation intermediate, this is not formed, we make the bromonium ion. We form the bromonium ion here. So we're doing an SN2-like reaction where we do have our nucleophile attacking the electrophile, leaving group leaving, but we bring in electrons from that electrophile to attack one of the carbons so that we can make this bond right here, so that we end up with full octets for everything. So the bromonium ion allows us to avoid making that electron deficient carbocation. Questions there?
Doctor, so then they're both SN2 reactions, correct?
Yeah, so this is really an SN2, right? We have our nucleophile attacking our electrophile, leaving group leaves. Just those two arrows, that's what we usually see for SN2. So we call this SN2-like for this reaction because it's not truly an SN2. We have another arrow coming in so that we don't end up with that carbocation there. So for this bromonium ion, it is very rigid. Also, bromine is a large atom. Bromine is a large atom. So if we have this really large atom and we have this rigid structure, this rigid three-membered ring, what is going to happen with the bromide, right? We have bromine with this positive charge and the bromonium ion. We have bromide with this negative charge. That's going to be our nucleophile. And we have these two carbons that are electrophilic. Right? Because bromine has a partial negative. Even if it has a full positive charge, it has a partial negative. And so both of these carbons end up with a partial positive. So our nucleophile can attack either of these electrophilic carbons, and our leaving group will leave. So in this reaction, we have the bromine attacking from the opposite face to where the bromine of the bromonium ion is. Bromonium ions at the top, bromide attacks from the bottom. Bromonium ions at the bottom, bromide will attack from the top. It's the opposite face, and so when we open this three-membered ring, it's an anti-addition. It's stereospecific, and it's an anti-addition. We are only going to add the bromide to the opposite face to where the bromine with the positive charge is. So we end up with these two products where, again, as we said before, anti-addition. So I've already shown you this, that it is an anti-addition. Why is it an anti-addition? Well, because of this bromonium ion. If we had the reaction occurring where we saw this as a product, if we saw this as a product, we would know this would be the syn addition product. But this is not observed. The syn addition product is not observed. We only see the anti-addition product. So we know we have to have the bromonium ion. If we had this, remember this intermediate that I showed you before, just one slide ago? If we had this as our intermediate, then that would allow for the bromide to attack from the top or the bottom of this carbocation, right? Top face or bottom face. And so we would get some syn and some anti-products formed. We would expect to have both syn and anti, where if it attacks from the top, then the two bromines are on the same face, so that would be a syn addition. If it attacked from the bottom, then they would be on opposite faces, but we would get this mixture of the two. We don't see a mixture of the two. We see no syn product, and so we know we have to have this bromonium ion. Because we don't see any of the syn products, we have to have the bromonium ion. If the carbocation was the intermediate, we would see both the syn and the anti, but we do not see this. Questions there?
Yes, the bromine ion intermediate where it makes the ring. How is it positively charged there if it has the partial negative charge. Is this you have these?
This is a formal charge. So remember, what we do for formal charge is 7 valence electrons minus 6 lines and dots around it. So it has to have a formal charge of +1, but so that's how we get a positive charge, but it always is electronegative. Electronegativity doesn't change.
Got it. Thank you.
All right, let's look at this. Oh, someone asking something?
Excuse me. I do, Dr. Nalbandi. I have just one question. Now, you mentioned on the last slide that, let's see, the 3-membered ring opens stereospecifically anti. Now, does that occur for all 3-membered rings?
That occurs for when we're opening the bromonium ion. When we add bromine, we are doing a stereospecific addition, where one of the bromines gets added to the top face and one of the bromines gets added to the bottom face. They get added in 2 separate steps, right? One bromine gets added in the first step and the second bromine gets added in the second step. But as they get added anti to one another, not syn to one another.
Awesome. And then would the excuse me, would this hold true for any 3-membered ring that we were encountering?
No, because those are different reactions.
Okay.
So different mechanisms will have different reactions. So yes, if there's a chlorine in this 3-membered ring, then yes, that is going to be true. But there are different mechanisms that we'll discuss.
So this would be true for like haloalkanes and these types of reactions.
If you're going to make this vicinal dihalide, where it's either bromine or chlorine, then yes, this is true.
Awesome. Thank you.
All right, let's look at this reaction in a little more detail. So we already saw this before. I showed you this a few slides before, that cis-2-butene, and we said it makes this racemic product. So I want to show you this mechanism so that you can know what is happening here. So we start off with our cis-2-butene, and we have our bromine, which we polarize. And so when we polarize it, I'm going to put a partial positive on one of the bromines and a partial negative on the other. I'm pulling electron density toward the bromine on the right. So I draw 3 arrows, one from the middle of the bond to the bromine that I've marked with the partial positive, one from the middle of the bond to the bromine, and the other from a lone pair on that electrophilic bromine to one of the carbons. So from the lone pair on the electrophilic bromine to one of the carbons. Remember, this is cis, so I still need to maintain that stereochemistry in my product. And so as I draw this, I can either draw both of them as a wedge or both of them as a dash. I'm going to draw both of them as a wedge. And I'm going to have bromine in a 3-membered ring. 2 lone pairs. Remember, always show all of your lone pairs. I saw a lot of you doing this kind of thing, just one lone pair and a negative charge. No. No. Show all of your lone pairs because that's where the reaction can occur. You need to know where you have lone pairs. So here we have bromine, 2 lone pairs, which tells us it has a positive charge based on its formal charge. The other ways that we could represent this same thing, so if you had drawn this as this is fine, or this is fine, or this. These are all the exact same thing. You have to show both of those methyls being on the same face, but it could be straight up and down, it could be pancake flipped, it could be down this direction with the bromine down, and then the pancake flip of that. All of those are the exact same thing, but we have to make sure both of our methyls end up on the same face. We know that there are hydrogens there, right? I didn't show them. But you know that what we really have is this. where we have our hydrogen in the back because our methyl's in the front. This is really the bromonium ion, but I'm not going to show the hydrogen because this is 352 and we know things now, right? So we have a bromonium ion. If I put this bromine with the positive charge at the top, then the bromide has to attack from the bottom. If I put the bromine with the positive charge at the bottom, the bromide would attack from the top. It would attack from the top because it has to attack on the opposite face to where the bromine is because this is large and it is rigid. So what are our arrows? So I will go from one of the lone pairs to one of these carbons. So I'll call this 1, 2, 3, 4. When I attack that carbon, it has an octet. That was why we did this, right? It has an octet. So something has to break. We break this bond. So from the middle of the bond to bromine. So bromine becomes kind of a leaving group. So this first reaction was SN2 like, but this is an SN2 reaction. Nucleophile, electrophile, leaving group leaves. So I'll label each part. So we have our nucleophile, we have our electrophile, and we have our leaving group for the SN2 reaction. So what happens with the SN2? We get inversion of configuration. We get inversion of configuration. So we need to show the stereochemistry in the beginning so that we can invert that configuration. So at carbon 3, nothing happens there. Carbon 4 is still wedged, still pointed down. And now we have bromine, and I'm going to draw this over, pointed that direction, pointed to the right, because we've broken that bond between bromine and carbon 2. But we still have the bromine carbon 3 bond. Nothing happened to that. So now looking at carbon 2, what has occurred? Well, bromide has come in from the bottom, and so I'm going to draw it in like this because it came in from the bottom. But now look at this. At carbon 2, only at carbon 2, where the reaction is occurring, we're getting inversion of configuration. So at carbon 2 now, we're pushing up what was attached there. And so now our methyl is still on a wedge. It doesn't change from a wedge to a dash. It just goes from pointed down to pointed up. The umbrella, right? The umbrella getting inverted. So this would be our product here. Or if I draw all 4 of these carbons in the plane, which is what I want to do, I want to draw the 4 carbon of the chain in the plane, and I want to have bromine either pointed toward me or away. So bromine's on carbon 2 and bromine's on carbon 3. So let's look at this starting structure. You should be able to see that I'm rotating this methyl downward. It's in the front. There's a hydrogen in the back, so I'll draw it in. I shouldn't need to, but I'll draw it in. There's a hydrogen in the back, so I'm going to rotate that methyl downward so it can end up here. As I rotate that methyl downward, hydrogen and bromine will be at the top. Hydrogen and bromine will be at the top. As I rotate one thing down, hydrogen goes to the front, bromine goes to the back. You should be able to visualize this. So what do we have? We have bromine here at the top on carbon 3. That's where we want our bond to carbon 4. We want that at the top. At the bottom on carbon 3, we want hydrogen and bromine. So I'm going to rotate here. I can rotate this direction. And so as I rotate my methyl up, then the bromine gets pushed down and the hydrogen gets pushed to the front. And so my bromine is again in the back. If you can't see this, you need to build a molecular model and rotate things. And you can just color code it, but you need to build a molecular model. So I'm going to tell you that for this molecule, this is SS. So let's do the opposite. So we have here the exact same intermediate. The exact same intermediate, positive charge. This is still 1, this is 2, 3, and 4. So if I have my bromide attack carbon 2 in one case, let's have it attack carbon 3. Because there's no difference, right? They're both electrophilic. So I'm going to have it attack carbon 3, and I'll break the bromine carbon 3 bond now. So now I get still an SN2, still inversion of configuration, but now this is at carbon 3. So if it's at carbon 3 now, what happens? That methyl gets pushed up, carbon 4, and bromine is here on carbon 3. But nothing happened at carbon 1, I'm sorry, at carbon 2. So I keep carbon 1 pointed down because I don't get inversion of configuration there. And I keep that carbon-bromine bond that I had originally. So this would be my product, or again, I want to draw my longest carbon chain in the plane, and I want to have the smaller groups pointed toward me or away. So the same thing that I did before. I'm going to get this now, and I'll leave you to do that yourself. But this product is R. So what did we get? The RR and the SS product attacking either side. They're both as likely. There's no preference for attacking carbon 2 or attacking carbon 3. So we get a 1-to-1 mixture of the two enantiomers. So we get a racemic mixture. So SN2, inversion of configuration. So we need to show stereochemistry to show that inversion of configuration. But the nucleophile attacks from the opposite face from where the bromine is. Questions on this?
Yes, Dr. Ambani, you said there's going to be an inversion of configuration at C3,
Yeah.
but why do we still have the wedge? Sorry, the wedge again at C3?
Because it's still a wedge, nothing changed there,
Good.
right? We have a hydrogen down here, and we have carbon 4 down here. So
What about C2? Why did we have dash line there again?
wait. So carbon 4 and hydrogen on carbon 3. And so we still have those two things. We still have a hydrogen on carbon 3. And we have our carbon 4. So there's our carbon 4. Here's our hydrogen. Those two things are there. They just get pushed up. As the bromine comes in, the umbrella gets pushed up. What's on one side doesn't switch sides. They're not going to switch sides. They're just going to go up. They go from down to pointed up. That's it. So hydrogen is on a dash line. Methyl's on a wedge. They stay as is. They just get inverted. They just get pushed upwards.
Oh, but in the C2.
Same thing for carbon 2. There's a hydrogen there on carbon 2, and that also gets inverted up. Same thing is happening.
But you said on the OR example, you drew dash lines on the bromine.
For this,
Yeah.
for the R example, the bromines, now once you get this product, these are the exact same thing. It's just rotating around. They're the exact same product. This is this. They're the same thing. It's just different conformations.
Can you draw the dash line for the SN2 at C3 as well?
Can I draw the dash line? This product? No. Unless we pancake flip it. So if you pancake flipped it, then you would get this and this, but that's not the same as this. These two are not the same. Up here and this, they're not the same, and you can build a model but they're two different things. They're non-superimposable mirror images of each other. But this is still going to be R, this is still going to be R. But I'm going to let you build the model and go back and do all that yourself, because that's review stuff. All right, any other questions before we move on?
I have a question. Which one would be more stable, the bromine on the wedge or the bromine on the dash?
There's no stability here, right? They're the exact same thing. These are enantiomers of one another. Everything's the same, so there's no difference. These aren't diastereomers where one is formed in, a higher proportion. They're formed in a one-to-one mixture. There's no difference. It doesn't matter if it attacks at carbon 2 or carbon 3, it's going to do both things. 50% of the time, it's going to do this, and 50% of the time, it's going to do this, because they're equally likely. All right, this is 12-6 now. So we were using bromine as the nucleophile, but we can use other nucleophiles. So we know that this is a good nucleophile, but we can actually use poor nucleophiles like water. So we can use water. We know that that's a poor nucleophile, but it's a nucleophile if nothing else is around. So if we run the reaction in water instead of carbon tetrachloride, then we have a lot of water around. It's not a good nucleophile, but if that's all we have around, if we have a lot of that around and we don't have a lot of the bromide ion around, then the water will react. So we will make our bromonium ion. So notice here, when the alkene is in a ring, we draw our bromonium ion like this. Or like this. We have the bromine in and out of the plane, and we keep the ring, the 5-membered ring or the 6-membered ring, in the plane. When we had so let me just go back to remind you, when we had this that was an acyclic alkene, we showed the stereochemistry of the two methyls, right? We did wedge dash with the methyls. Acyclic alkene, we ended up with wedge dash for the methyls. But here, when we have an alkene that is a cyclic alkene, then we do wedge dash with the bromine of the bromonium ion. So two different things, two different scenarios to show the stereochemistry. So we have our poor nucleophile that comes in. Yeah, there's some bromide around. It's around, but we don't have a lot of it. We have an excess of water. So we have a lot of water around from the lone pair on oxygen to one of the sides of this bromine, opening up this ring. Right? A 3-membered ring is very unstable, so we open up that 3-membered ring where we get inversion of configuration. So if I call this carbon 1 and I call this 2, we get inversion of configuration only at carbon 1. Carbon 2, look at the configuration there, hydrogen, bromine, bromine's on a wedge, hydrogen's on a dash, nothing changed there. But look at this, hydrogen has to be on a dash if the bromine in this bond, carbon 1, bromine bond, is a wedge. But now this hydrogen goes from being on a dash line to being on a wedge. We get inversion of configuration. The oxygen attacks from the opposite face to where the bromine is. So the oxygen is attacking from the back. Oxygen is attacking from the back. And so as it attacks from the back, it pushes the hydrogen to the front. And so we see this hydrogen over here in the front, and we get an oxonium ion. What do we know about oxonium ions? We know that they are acidic, and so we can lose a proton. So from the middle of the bond to the oxygen, and then we end up with our alcohol. So this is called a 2-halo alcohol. because carbon 1, carbon 2, we have these, so here carbon 1 has the alcohol, carbon 2 has the halogen, so a 2 halo alcohol. So we end up with, look at our bromine in the front and our oxygen of the water, of the alcohol in the back. So it's still an anti-addition, just like what we were just showing. It's still an anti-addition because that bromine of the bromonium ion is so large, the water has to attack from the opposite face. The water attacks from the opposite face. So we get this product here. They've only shown you one, but if we just write racemic underneath it and we show stereochemistry, the other product is also possible. So the other product, you know what the enantiomer is. It would be bromine on a dashed line and the alcohol on the wedge. I don't need to show those hydrogens, you just know they're there. But if we write racemic, we show stereochemistry for one and write racemic underneath it. As long as they are enantiomers of one another, then we can write racemic underneath it. So if we did that with water, then we can probably do the same exact reaction with an alcohol instead, giving us an ether. So what is this reaction? Here we have this 6-membered ring, and so we end up with a 6-membered ring where now we're going to put bromine. And I'll put bromine as a wedge here. But again, it's equally as likely that the bromine is on a dashed line. And so here, it doesn't matter which side gets attacked, but we need to show the lone pair attacking that carbon, electrons get pushed up. And so we stay with our bromine on a wedge, just like we see here in the product, but we get inversion of configuration where our oxygen gets added to the opposite face. It still has the hydrogen, it still has the methyl, so now the oxygen, one lone pair, positive charge. What did we start off with? Something having a positive charge, so something has to have a positive charge, right? We keep it positively charged throughout. So then I can just draw this arrow to the oxygen where I have lost a proton, which ends up with giving us this product where, again, it was an anti-addition. But as we've shown it, remember, this is racemic. So the opposite configuration is just as likely. This is racemic, both enantiomers, and this is racemic. So they just write trans, and remember, trans just means these two things are on opposite faces, but it's just as likely for us to do the opposite configuration, one-to-one mixture of the two enantiomers. Questions there? All right, so we have our reaction where we can make a vicinal halo alcohol, right here, vicinal halo alcohol. We know the reaction, we use water as a solvent instead of carbon tetrachloride. We use chlorine gas, but it can be used to make the chloronium ion instead of the bromonium ion. The chloronium ion is made. And so in that reaction, we can add in base and water, and we can make an oxycyclopropane. You remember the oxycyclopropane, a 3-membered ring with an oxygen in it. So what is happening here for this mechanism? So first we have our cyclohexene reacting with chlorine. And so just as we saw before, we're going to polarize, so partial positive, partial negative. So from the middle of the bond to the chlorine, middle of the bond to chlorine, and then we need a third arrow from a lone pair to one of those carbons, which gives us this as a product. So I can do this dashed line with a positive charge, But you know that this is racemic. You know that the enantiomer exists where the chlorine is on wedges. Wedges instead of dashes. So we just write racemic underneath this. Then we have water, which will come in and attack. And so the water, I'll draw it here from the lone pair to one of those carbons. It doesn't matter which one, but here, I'm just going to draw it to this carbon just because that's where the OH ends up in the end. So our chlorine stays on a dash line, and our oxygen gets added on the wedge. It's adding to the opposite face. We know that that oxygen will have a positive charge. It's pulling away electron density, partial positive here, partial negative also on that oxygen. So we pull away electron density. So I can say minus a proton, and we end up with this as our product. This is just after the first step. This is our full mechanism for the first step. So in the second step, so I'll just redraw that product because I want to show that bond to hydrogen. So what do I have here? I have a carbon that has a partial positive because it's bonded to chlorine, and I have an oxygen that has a partial negative because it's bonded to this hydrogen that's making this hydrogen very acidic. So if I add in sodium hydroxide, what's going to react there? It's the hydroxide, right? The OH with a negative charge. Sodium is just hanging out. So this strong base does what bases do. It goes to pick up the proton. And so we end up with this intermediate where we have our oxygen now with a negative charge. So as I said before, we have a carbon that is an electrophile. We have a chlorine that's a leaving group, and we have an oxygen that is a good nucleophile. It's also a strong base, but because we only have something electrophilic around, it's not going to act as a base, it's going to act as a nucleophile. So what are we doing? We're doing an SN2 reaction. From the lone pair to this carbon, from the middle of the bond with our chloride leaving. And so we end up with this three-membered ring. The oxygen has two lone pairs left on it. So we know it's neutral, not a positive charge here, it's neutral, but it's on a wedge for both of the bonds. It was in the front. What else was in the front here? We had a hydrogen that was in the front, right? And that hydrogen is now in the back on this carbon. Inversion of configuration at that carbon because it's an SN2 reaction. So we end up with this product. This product an internal mirror plane. So what does that make this? Meso. Meso product. But we said this was racemic. This is also racemic, as is this. So the other enantiomer there. This is also racemic, but then we end up with a meso product in the end because we have no stereochemistry, because we have this internal mirror plane. But if I gave you this molecule, so still cyclohexene, but then I put a wedge here. And we did the same two steps. So one step is the chlorine and water. And then the second step is the sodium hydroxide and water. then what would happen here is that we'd still end up with this as our product. But we'd also get this as a product. And what's the relationship between these two? These two are diastereomers. So they are formed in unequal amounts. Unequal amounts. If we drew the other thing here, dashed line, these two are identical, right? Because it is meso. These two are identical. They're not enantiomers of one another. They are identical. So they are superimposable mirror images. But here we would get diastereomers formed in unequal amounts if we had some other stereochemistry elsewhere. Questions on this? All right, so we've been talking about these alkenes that are symmetric. What happens if they are unsymmetric? What is going to happen? Well, the reaction is regioselective. This reaction is regioselective. So if we have these carbons, so if I call this 1, 2, 3, 1, 2, 3, 1, 2, 3, we have a choice between adding bromine to carbon 1 or carbon 2. Adding the alcohol to carbon 1 or carbon 2, or the nucleophile, we'll say, whatever the nucleophile is. It could be bromine, it could be alcohol, it could be water. Any kind of a nucleophile there. But we add our nucleophile to either carbon 1 or carbon 2. We add our electrophile to either carbon 1 or carbon 2. It turns out that we only get this product here, 1-bromo, 2-methyl, 2-propanol. We don't get any of the product where the alcohol has been added to carbon 1 and the bromine to carbon 2. None of this. What's happening here is that this is regioselective. The reaction is only going to occur where we have our nucleophile attack the more substituted carbon. The attack happens at the more substituted carbon. So here our nucleophile is water, but it could be any nucleophile. It's going to attack the carbon here that has the 2 methyls on it versus the carbon with 2 hydrogens. So it attacks the more hindered carbon because that has more partial positive. Based on hyperconjugation, more of the alkyl groups are donating in more electron density, so we get more partial positive there. And so then we can break the bond there between bromine and that more hindered carbon, which puts our bromine on the less hindered carbon. Bromine stays attached. So if this is 1, 2, one of these methyls is 3, bromine stays attached to carbon 1, and the oxygen gets added to carbon 2. So then we know our last step, if we use water or alcohol, is to deprotonate. And so then our nucleophile has been added to the more hindered carbon and our electrophile to the less hindered carbon. This is following Markovnikov's rule. We already saw Markovnikov's rule, right? We said H goes where there are more H's. Well, now we can expand it to say, instead of just H, we can say, or any electrophile will go where there are more H's. H will go where there are more H's, but really any electrophile will go where there are more H's. So our electrophile gets added to the to carbon 1, right? This is our electrophile. And this was our nucleophile. The nucleophile will get added to the more hindered carbon. It's just between carbons 1 and 2, though. It's just between the 2 carbons of the alkene. But our nucleophile gets added to the more hindered carbon, and our electrophile goes where there are more H's. It goes to the less hindered atom. So if you're just drawing the product, you can just predict the product. You don't even need to do the mechanism. But we are going to be attacking the more hindered side. So this also leads to another rule. Remember when we had our oxycyclopropane, right? We had this kind of thing. This is neutral. So when you have a neutral ring, then your nucleophile will attack the less hindered side. But if you have something that has a positive charge, so here, you know, there's a positive charge on that bromine, so we have a positively charged ring, then your nucleophile is going to attack the more hindered side. This is just what they prefer to do. So look at the ring. Is it neutral? Oxycyclopropane that's neutral, then the nucleophile will attack the less hindered side. We learned about that last semester. But if we have a positively charged ring, then the more hindered side gets attacked. So pay attention there to what kind of ring you have. Questions? All right, so we've seen this reaction with, we had bromine, we had chlorine. We have other reagents where we can add the two atoms also. So here, A is always your electrophile, and then B is your leaving group that becomes your nucleophile later. Your leaving group that becomes your nucleophile later. And so here they give you a bunch of different examples where you can see that in all cases, based on Markovnikov's rule, H or the electrophile goes where there are more H's. And so with the starting material where we have these two H's on one carbon and no hydrogens on the other carbon, the electrophile is going to go where we have more H's, and the nucleophile will be added to the other carbon of the double bond. So look at your starting material. 2 hydrogens on this carbon, electrophile gets added here. No hydrogens here, the nucleophile gets added there. Questions on that?
Yes, Professor. So you said that for regarding any H, it's going to go to the more H. Does that imply to, let's say, if there is more than one compound reacting?
No, we're only talking about one compound reacting. We're talking about one alkene. For this is the end of 12-6. We're skipping 12-7 to 12-9. You can read through that. It's good information. So you're not going to be tested on what's in 12-7 to 12-9, but I'd recommend still reading it. Hopefully you already read chapter 12 all the way through. But then we will start with 12-10 on, what's today? Wednesday? So Friday. So we're getting close to the end of this chapter. So again, we have a lot of reactions we're going to go through. So make sure you are reading and rereading, doing the homework, and then make sure once we get closer to the end that you do the learning checks ahead of time so that you can check your work rather than having to scribble everything down furiously as I go through them. All right. Any last questions? All right, you guys. Well, that's it for today. I'll see you guys for lab and office hours. I did grade your problem set, so make sure you look at that before office hours if you have it later this week, and correct whatever you can. But I will talk to you guys soon. Love you guys. Have a good day. Bye. You're welcome. Bye, you guys.
Thank you.
I have a question about lab.